Welcome to the deep dive.
Oh,
So, you want to learn more about Linux?
yeah.
Its file system, boot process, user management, and networking basics.
Yeah.
So we're going to go on a deep dive today into the heart of Linux,
Right.
exploring its intricate parts, how it all works,
Yeah.
like opening up a finely crafted watch
Okay.
to see all the gears turning. Expert speaker, ready to be our guide.
Absolutely. Yeah, your sources are jam-packed with fascinating technical details.
Yeah.
It's going to be fun. Think of it this way. We're going to
Yeah.
decode the magic of a Linux system, right?
Yeah.
We're going to see how seemingly complex things like device management or user permissions and even shell scripting
Right.
fit together
Yeah.
beautifully.
Okay, let's start by imagining a Linux system, like a two-story building.
Right.
The kernel at the very bottom in kernel space
Yeah.
is like the building's foundation, handling all the core functions.
Okay.
And everything we do as users, along with our apps, happens upstairs in user space.
It's a clever design. The kernel, down in the basement, directly interacts with the hardware, right?
Right.
Your CPU, memory, hard drive, like a meticulous landlord managing every aspect of the building.
Right, so we're like, the tenants upstairs, we can't just go down and start messing with the wiring.
Definitely not. It would be chaos.
Right.
Instead,
Yeah.
we make requests to the kernel through what are called system calls. Every time you open a file or
Yes.
you connect to the internet, your applications are essentially slipping a note under the kernel's door, asking for something to be done.
I see. And the kernel, being the efficient landlord, takes care of those requests.
Precisely.
This separation is what keeps Linux organized and secure.
Yes.
I love this visual our sources gave of picturing it like an onion with the kernel at the center.
Yeah.
It's like, those Russian nesting dolls
Yeah.
with each layer building on the one before.
Yeah, that's a perfect analogy. Applications like your web browser are on the outermost layer.
Okay.
Utilities are somewhere in the middle. Essential services are closer to the kernel, at the core.
Okay, so we've got our two-story building, our onion, or our nesting dolls. Now let's focus on that core, the kernel.
Okay.
It's got a lot on its plate, right?
It does.
Our sources mention process management, memory management, and device management.
Yeah.
It sounds like a full-time job.
It certainly is. The kernel is like a master juggler.
Okay.
Take process management, for example.
Yep.
You might have dozens of programs running,
Yeah.
music playing, browsing the web, editing a document, whatever.
Right.
The kernel makes it look like they're all happening at the same time,
Right.
even if you only have one CPU.
Yeah, so it's constantly switching between these different tasks,
Yeah.
giving each one a tiny slice of time on the CPU, almost like a chef
Yes.
in a busy kitchen, tending to multiple dishes at once to create a seamless meal.
And what's fascinating is that on a multi-CPU system,
Yeah.
the kernel can become even more of a pro, so to speak, because it can assign different processes to different CPUs, making sure that everybody gets their fair share and maximizing the use of your computer's power.
So next up is memory management.
Okay.
It's like the kernel's running this giant library,
Yeah.
keeping track of where all the data and programs are stored.
The kernel's like a super organized librarian.
Okay.
It keeps a record of which parts of the memory are free and which are being used.
Okay.
And just like a library has restricted sections, the kernel has its own
Okay.
private memory area, which is off limits to the users and their applications. It's all about security and stability.
Makes sense. You wouldn't want rogue programs snooping around
Yeah.
in the kernel's secret archives. So speaking of managing things,
Right.
what about all the devices connected to our computers?
Yeah.
Keyboards, mice, webcams, hard drives.
That's where device drivers come in. They're like specialized translators.
Okay.
Each device speaks its own language, you see?
Uh-huh.
And the driver acts as an interpreter, allowing the kernel to understand and communicate with the device.
So my printer driver is like a Rosetta Stone
Yes.
between my Linux system and the printer itself.
Exactly. And what's really elegant is how Linux represents all these physical devices
Okay.
as files within the file system,
I-
using device files or device nodes.
Okay.
You can find them all neatly organized in the dev directory.
So instead of me having to write complicated code to talk to my hard drive,
Right.
I can just treat its device file like any other file in the
Yes.
system.
Precisely. For example, DEVSDA usually represents your primary hard drive.
Okay.
And if you've ever used a text-based terminal, that's interacting with a device file like devd1, which represents the first virtual console.
Our sources mentioned this command DD that lets you interact with these devices directly.
Yeah.
Sounds powerful,
Yeah.
but a bit like playing with fire.
It is powerful.
Yeah.
It's a low-level data transfer tool.
Okay.
You can copy an entire disk image to a USB drive with just one command.
Why?
But be warned, it's a powerful tool
Yep.
that needs to be handled with care.
Okay.
One wrong move, and you could overwrite critical data.
Okay, I see how that could be a disaster.
Yeah.
The sources also mentioned this udev, which sounds much friendlier.
udev is like a smart device manager. You see, in the past, device naming in Linux could be messy
Okay.
with names changing if you added or removed hardware.
Right.
So udev came along
Right.
and brought order to the chaos.
Okay.
It ensures that the device names are consistent no matter what changes you make to the
Nice.
hardware.
So udev is making sure that our devices have proper names and addresses,
That's a good way to put it.
so to speak.
Yeah.
So everything runs smoothly.
And what's even more fascinating is that udev can automatically configure devices based on their attributes, like serial numbers or vendor IDs. It's like having a personal assistant for your hardware.
That's impressive.
Yeah.
So speaking of organization, let's talk about file systems.
Yeah.
This is the way Linux organizes data on our hard drives
Right.
and other storage devices.
File systems are the backbone of data storage in Linux.
Okay.
Imagine a giant library filled with books.
Okay.
That's your hard drive. The file system is the system of shelves and catalogs and labels that keeps all those books organized so you can find what you need.
And that organization is based on this familiar tree-like structure we all use with a root directory, branches for subdirectories, and leaves representing the files themselves.
Exactly. Over the years, Linux has developed several types of file systems.
Okay.
With the extended file system series, x22, x23, xt4 being the most widely used.
Our sources highlight some key differences between them, focusing on this thing called journaling in X3 and improvements in X4. What exactly is journaling?
So imagine having a logbook in our library that tracks every book that's borrowed and returned.
Okay.
That's essentially what journaling does for a file system. It keeps a record of all the changes. So if the system crashes unexpectedly, it can use that journal to restore the file system to a consistent state.
Wow.
It's like having an undo button for your hard drive.
That sounds like a huge improvement for data safety.
Right.
What about X4? How does that build on journaling?
Well, X4 takes journaling to the next level, you see.
Okay.
It also adds support for much larger files and much more efficient handling of large directories. Think of it as an upgraded library with more space and a faster, more streamlined cataloging system.
I also see this command mkfs. Is that how you actually build one of these file systems from scratch?
Precisely. Once you've partitioned your hard drive, MKS is what you use to format each partition with a specific file system type, getting it ready to store data.
Our sources also emphasize this importance of mounting and unmounting file systems.
Right.
Why are those actions so critical?
Okay, think of it this way. You have this beautifully organized library, but it's in a separate building. Mounting a file system is like building a bridge between that building and your main house.
I see.
Allowing you to access all those books. Unmounting is like retracting the bridge. Ensuring that you can safely close down the library without anybody getting trapped inside.
Okay, so mounting a file system is essentially connecting it to the main file system tree. Making all its files and directories accessible.
And unmounting disconnects it, ensuring data integrity and allowing you to safely remove or disconnect the storage device. Linux provides these commands mount and mount for these operations.
Our sources mentioned this file, etc. stab.
Yes.
Which sounds like it's related to this whole mounting process.
It is.
What exactly does this file do?
Okay, think of etc. stab as a set of instructions for your system. It tells your computer which file systems should be automatically mounted at boot time and where they should be mounted. It's like having a dedicated librarian who automatically opens up all the important sections of the library every morning.
So that saves a lot of manual work.
It does.
You wouldn't want to have to mount all your file systems every time you turn on your computer.
Exactly. Etc. stabin ensures that all your essential file systems are ready and available when you need them.
Okay, our final topic in this section on file systems is a bit more technical.
Okay.
It's file system integrity checks using FLEC.
Yeah.
Why are these checks important and how are they done?
Well, even the most well-organized library can have the occasional misplaced book or torn page.
Right.
Fleck is like a meticulous librarian who inspects the library for any errors or inconsistencies.
Okay.
It's a command line tool you can use to scan a file system for any potential problems and attempt to repair them.
So you're saying Fleck is like running a diagnostics test on your hard drive?
Precisely.
Okay.
It's especially important after an unexpected system crash.
Right.
Or if you suspect any file corruption.
The sources mention using the NAF-P option for automatic repair. Does that mean Fleck can fix problems on its own?
Yeah, you can think of the NAF-P option as giving the librarian the authority to fix minor issues, like misplaced books.
Right.
But for more serious damage, like a fire or a flood in the library, Fleck might need your input.
I see.
Or it might not be able to fix things automatically.
Now, before we move on to the boot process, can you briefly explain what swap space is?
Okay.
Our sources mention it as being connected to the concept of memory.
Imagine our library has a limited number of reading desks, right?
Okay.
When all the desks are occupied, some people might have to work in a less comfortable overflow area. That's kind of what swap space is like.
Okay.
It's a designated area on your hard drive that acts as an extension of your RAM.
Okay.
When your system runs out of physical memory, it can move less active data to this swap space,
I see.
freeing up RAM for more urgent tasks.
So it's like a temporary holding area for data that isn't being actively used.
Exactly.
Allowing your computer to feel like it has more memory than it actually does.
Precisely.
Yeah.
But keep in mind that accessing data on a hard drive is much slower than accessing it in RAM. So while swap space is helpful, it's best to have enough physical memory to avoid relying too heavily on it. Excessive swapping can make your system feel sluggish.
It's always good to have enough desks in the main reading room.
Exactly.
Okay, I think we are ready to move on to the next section.
All right.
The Linux boot process. This is that sequence of events that happens when you turn on your computer, bringing it to life.
Like waking up a sleeping giant.
Our sources describe this process in stages. First, the BIOS or UEFI firmware on your motherboard takes control, like an alarm clock going off, and performs some initial hardware checks, making sure everything is in order.
And then comes the bootloader, a small program with a big job. It's responsible for loading the operating system kernel into memory. Think of it as the conductor of an orchestra, bringing in the musicians and getting ready for the performance.
And once the kernel is loaded, it takes over, like the conductor raising their baton.
Yes.
And it starts initializing devices, mounting the root file system, and setting the stage for all the user space activities.
It's an intricate process happening in the blink of an eye. A perfectly orchestrated sequence, leading to a fully functional system.
Our sources focus on GRUB as the most common bootloader.
Yeah.
What makes GRUB special?
Well, GRUB is like a multi-talented maestro, so to speak.
Okay.
It can boot multiple operating systems, not just Linux. Imagine being able to choose between different orchestras each morning.
That's amazing.
Yeah. And it also allows you to pass special instructions to the kernel, kind of like giving the conductor notes on how to interpret a particular piece of music.
I see.
And it even provides this menu-driven interface. So you can easily select different boot options.
That's really versatile.
It is.
Our sources even delve into the internal workings of GRUB and its various boot stages.
Yeah.
It's fascinating to see the level of complexity involved in something we take for granted.
It's a testament to the elegant design of Linux.
Right.
The boot process may seem like magic, but it's a carefully choreographed dance of hardware and software, each playing its part to perfection.
All right, now that we've covered the boot process, let's move on to user management and permissions.
Yeah.
This is how Linux keeps track of who's using the system and what they're allowed to do. Ensuring everybody plays by the rules.
Exactly. It's like a well-run organization with clear roles and responsibilities. Linux uses a system of users and groups to control access to files and resources, preventing unauthorized modifications and maintaining security.
Our sources highlight this crucial file, etcetera root.
Yes.
What kind of information does it hold?
Think of etcetera as a secure registry of user accounts. It's like a detailed directory of everyone who has access to the system. It stores usernames, passwords, in a securely encrypted form, of course, user IDs, their home directories, and even their default shells.
I can see why you wouldn't want unauthorized users tampering with that file.
Absolutely not. In addition to user accounts, Linux also uses the concept of groups.
Okay.
Users can be members of one or more groups.
Yeah.
And group membership can be used to grant or deny access to specific resources.
Right.
It's like having different departments within an organization, each with its own set of permissions.
So it's all about keeping things organized and secure.
Precisely.
Ensuring that only authorized personnel can access sensitive information.
And when it comes to files and directories, Linux uses a granular system of permissions to control who can read, write, or execute them.
Okay.
It's like having a set of keys that determine who can open which doors in our library.
Our sources mention the chmod command as the tool for modifying these permissions.
Yes.
Can you explain how that works?
Chmod is like a master key maker.
Okay.
It allows you to set permissions for the owner of a file, the group that owns the file, and everybody else.
Right.
You can use letters like R for read, W for write, and X for execute.
Okay.
Or you can use numbers that represent combinations of these permissions.
So if I want to give everyone read access to a file, I would use chmod a +R file name.
Yes.
And if I want to prevent anyone except the owner from writing to a file, I would use chmod gow file name.
You got it. It's a simple yet powerful system for managing access control in a Linux environment.
All of this is really starting to make sense.
Yeah.
Now let's move on to shell scripting basics.
Okay.
Our sources describe it as a way to automate tasks in Linux.
Yeah.
Like having a personal assistant to handle repetitive chores.
Shell scripting is an incredibly valuable tool, you see.
Okay.
It allows you to combine multiple commands and execute them as a single unit, making it perfect for automating repetitive tasks, managing system administration chores, and handling batch processing.
Sounds like something any Linux user should have in their toolkit.
Absolutely. A basic shell script starts with this special line called a shebang, which tells the system which interpreter to use for the commands in the script.
Okay.
It usually looks something like #.binbash, indicating that the bash shell should be used.
Like giving the computer instructions on which language to use.
Exactly.
Okay, our sources mention some important concepts in shell scripting, like variables, quoting, and exit codes.
Right.
Can you give us a brief overview of these?
Well, you can think of variables as containers for storing information within your script.
Okay.
You can assign values to these variables and use them later. Quoting is important when dealing with special characters or spaces in your commands.
Okay.
And exit codes are how scripts signal whether they completed successfully or encountered errors.
So if a script runs smoothly and finishes its task, it'll exit with a code of 0.
Typically.
And any other exit code usually means something went wrong somewhere.
Exactly. It's a simple way for scripts to communicate their status.
Our sources were going to provide a basic scripting example to illustrate these concepts.
Right.
But I think we're getting close to the end of this segment. Perhaps we can dive into that in the next part.
Yeah, that sounds good.
Okay. So we've covered a lot of ground already.
We have.
From the foundational concepts of kernel space and user space to the intricacies of file systems and user management. It's amazing how all these pieces work together.
They do.
So seamlessly. We've explored the Linux system like this fascinating machine.
It is.
Understanding its core components and how they interact.
And we've only just begun. In the next part, we'll explore the world of shell scripting.
Okay.
And we'll dive into the fascinating realm of networking.
Yeah.
So we'll uncover the secrets of communication in a Linux environment.
I'm already looking forward to it. And listener, we hope you'll join us for part 2 of this deep dive, where we'll continue to uncover the magic of Linux.
I hope so too. Welcome back to our exploration of the Linux world.
We left off on the verge of diving into shell scripting. You were about to show us a basic example.
Right. Let's say you have a bunch of text files and you want to see their contents without opening each one individually.
Yeah.
We could create a simple script to do that for us.
Okay, that sounds handy. What would that look like?
Okay, so let's name our script filereader.esh.
Okay.
It starts with the shebang line, #.binbash, which tells the system to use the bash shell.
Right, like giving the computer instructions on which language to use.
Exactly. Then we use a special variable, $1, to capture the file name that is given to the script when it's run.
I see.
And finally, we use the cat command, which simply displays the content of a file.
So the entire script is just 3 lines.
That's the beauty of it. Here it is.
Okay.
#.binbash. Cat $1.
Wow, that's incredibly concise. So how would I actually use this script?
Okay, first, you save those 3 lines as a file named filereader.esh.
Okay.
Then you make it executable with the command chmod +X .filereader.esh.
Okay.
Now, you can run it like this. .filereader.ev or my document.txt,
Okay.
replacing my document.txt with the actual name of your file.
So the script takes the file name as an argument and then cats it out for me to see.
You got it. Shell scripting is all about efficiency.
Yeah.
And automating those tasks that would otherwise take multiple steps. And this is just scratching the surface.
Right.
Imagine incorporating loops to process multiple files at once, or conditional statements to make decisions based on the file's content.
Wow.
The possibilities are vast.
I can see how learning shell scripting can turn you into a real Linux power user.
It can.
It's like having a set of tools to build your own customized solutions.
Precisely. Now, let's shift our focus to the world of networking. Your sources describe the TCP/IP network model as the foundation of how data travels across the internet.
Right.
It's a big topic, so let's try to break it down.
It's amazing to think that every email, every web page, every video stream all relies on this underlying model.
It's pretty fundamental.
It sounds like it.
Think of the internet as this giant, complex postal system
Okay.
to get your data letters, so to speak, delivered accurately and efficiently.
Yeah.
We need rules.
Right.
And that's what the TCP/IP model provides.
Okay.
And just like a postal service has sorting departments, delivery trucks, and mail carriers, you know, the TCP/IP model is divided into layers, each with its own specific function.
Our sources mention 4 main layers.
Yeah.
Application, transport, network, and physical. It's like this well-organized hierarchy.
It is.
Ensuring everything runs smoothly.
Let's start at the top with the application layer.
Okay.
This is where you, as the user, interact with applications, like your web browsers, email, clients, chat programs, whatever. This is the layer that we experience directly.
So when I type a website address into my browser, that's happening at the application layer.
Exactly. Now, for your request to reach the web server and for you to receive the web page, the data needs to be reliably transported across the network. That's the job of the transport layer.
And that's where we encounter the famous TCP and UDP protocols, right?
That's right.
TCP is like this meticulous courier service, ensuring every package arrives in perfect condition and in the right order.
Yeah.
And UDP is more like sending a postcard, faster and lighter, but with no guarantee of delivery.
That's a great analogy. TCP is used for applications that demand reliability, like web browsing, file transfers, and email.
Right.
UDP is more suitable for streaming video or online gaming, where some data loss is acceptable and speed is critical.
Next, we have the network layer, which sounds like it's responsible for figuring out the best route for our data packets.
To travel across the internet.
It's like the Postal Service's sorting center, determining the most efficient path for your letter to reach its destination. The network layer uses IP addresses, which are unique identifiers for every device on the network.
Which brings us to IP addressing and subnetting.
Yeah.
Our sources explain how IP addresses are like digital street addresses for computers.
Exactly. Just like a postal address tells the mail carrier where to deliver your letter.
Right.
An IP address uniquely identifies a device on a network, allowing data to be sent to the correct destination. And subnetting is like dividing a city into neighborhoods or zip codes, making it easier to manage and route traffic.
So subnetting allows network administrators to break up a large network into smaller, more manageable segments.
Precisely. Each subnet has a subnet mask. Which helps determine which part of the IP address identifies the network and which part identifies the specific host within that network. Our sources also introduce a few command line utilities that can be used to explore and manage the network from a Linux system.
Tools like ifconfig or ipep let you see your network interface's configuration details, like the IP address, subnet mask, and more. Think of them as peeking into the network settings of your computer.
Right. And then there's ping, the trusty tool for checking if another device on the network is reachable.
It's like sending a quick hello signal to another computer and seeing if you get a response back. If you do, you know there's a working connection.
And what about traceroute? That one sounds interesting.
Traceroute is like mapping the journey of your data packet across the internet. It shows you the route it takes, hopping from one router to another until it reaches its destination. Imagine seeing all the postal hubs and sorting centers your letter passes through.
That's fascinating. It really gives you a sense of the vastness and complexity of the internet. Our sources also mention network address translation, or NAT.
NAT. This is especially important in home and small office networks. Imagine you have a family sharing one phone line.
Okay.
NAT allows multiple devices to share a single public IP address, much like having one phone number for the entire household.
That explains how all the devices in my home can connect to the internet, even though my ISP only gives me one IP address.
Exactly. Your router acts as a middleman,
Right.
translating the private IP addresses of your devices into the public IP address assigned by your ISP.
Okay.
To the outside world, all traffic seems to be coming from that single public IP.
So NAT not only conserves valuable public IP addresses, but it also adds a layer of security by hiding the internal structure of my home network from the outside world.
You got it. It's a clever solution to a common networking challenge.
This brings us to the crucial topic of firewalls.
Right.
Those digital guardians that protect our systems from unwanted intrusions.
Think of a firewall as a security checkpoint at the entrance to your network.
Yeah.
It carefully scrutinizes incoming and outgoing traffic. Okay.
Blocking anything that looks suspicious or unauthorized.
Our sources mention the Linux kernel's built-in firewall, iptables, which sounds like it gives you a lot of control.
It does.
Over what traffic is allowed in and out.
Iptables is like having this set of customizable security rules that you can apply to your network traffic.
Yeah, okay.
These rules are organized into chains,
Right.
and each chain represents a different stage in the packet processing path.
So you can create rules that say, block any traffic coming from this particular IP addresses.
Yes.
Or allow connections only to these specific ports.
Precisely. You can specify conditions like the source IP, the destination port, the protocol being used,
Right.
and then you can define actions to take if those conditions are met.
Okay.
Accepting the traffic, dropping it, or even logging it for further analysis.
It's like having a set of filters that sift through all the network traffic, ensuring that only the good stuff gets through.
And our sources recommend starting with a default deny policy.
Which means that unless you explicitly allow a specific type of traffic, it's blocked by default.
That sounds like a very cautious approach.
It is.
But probably a good one when it comes to security.
It's like locking all the doors and windows in your house.
Right.
And then selectively opening only the ones you need.
Yeah.
It forces you to be very deliberate about what traffic you allow, which is a good security practice.
Now, our sources go on to describe strategies for configuring firewalls for both individual machines and entire networks.
Right.
Protecting a single machine is like securing your own home.
Yeah.
You focus on configuring the INP-UT chain in iptables,
Right.
controlling what traffic is allowed to enter your system.
So you want to block any unwanted incoming traffic,
Okay.
like connections to ports that aren't being used for legitimate services.
But you also need to make sure that you allow traffic for the services that you do need, like SSH, if you want to be able to access your machine remotely.
Exactly. What about protecting an entire network?
Yeah, that sounds more complex.
Protecting a network is like securing a whole neighborhood.
Right.
You typically have a dedicated firewall device, like a router, positioned at the edge of the network.
Like having a guardhouse at the entrance to the neighborhood.
Precisely. This firewall device filters traffic between the internal network and the external internet. And because traffic flows in both directions, you need to consider both incoming and outgoing traffic.
So you might want to restrict outgoing traffic to prevent users on the internal network from accessing certain websites or services.
Yeah.
Perhaps for security or productivity reasons.
Exactly. And for incoming traffic, you would likely use a similar default deny policy, only allowing the traffic that's absolutely necessary for the network to function.
It sounds like building effective firewalls requires a deep understanding of network protocols.
It does.
Services and security best practices.
It does require some expertise.
Yeah, like becoming a network security expert.
But the good news is that there are plenty of resources available.
To help you learn and implement solid firewall strategies.
Okay.
And the effort is well worth it.
Yeah.
A robust firewall can significantly reduce your risk of being compromised.
Well, I'm feeling a lot more informed about firewalls now.
Good.
But I think we're nearing the end of our time for this part of the deep dive.
Okay.
Should we wrap things up here?
Yeah, that's probably a good idea. We've covered a lot of ground.
We have.
From shell scripting basics to the complexities of networking and firewalls.
We've seen how Linux provides the tools to not only understand the network, but also to manage and secure it effectively.
And there's still more to explore.
Right.
In the final part, we'll look at some additional fascinating aspects of the Linux world.
Okay, listener, we hope you'll join us for the final leg of this deep dive into Linux.
Yes, we've got more exciting discoveries ahead.
Welcome back to the final part of our Linux deep dive.
We've journeyed through the inner workings of Linux, from the core kernel to that vast network. And we left off discussing the importance of firewalls.
Right, those digital guardians. Right?
Yeah, those guardians of our systems.
Protecting from unwanted intrusions.
Our sources went into some detail about different firewall strategies, depending on whether you're protecting a single machine or a whole network.
You're securing a single machine. It's like fortifying your own home, right?
Right.
You focus on configuring that INPUT chain in iptables, which controls what traffic is allowed to enter your system from the outside.
So you'd create rules to block any unwanted traffic.
Exactly, like someone trying to, pry open a window,
Right.
sneak in through a back door.
Our sources really emphasize the importance of a default deny policy.
Yeah, a default deny policy means that unless you specifically create a rule to allow certain traffic, it's automatically blocked. It's like having a sign on your door that says, no entry unless invited.
That makes a lot of sense from a security standpoint.
You're not accidentally leaving any doors open, right?
Right.
To unwanted guests.
So that's for individual machines. What about protecting an entire network? That's like securing a whole neighborhood.
Exactly. In a network scenario, you typically have a dedicated firewall device, like a router.
Right.
It acts as the main security checkpoint.
It's like having a guardhouse at the entrance to the neighborhood.
A good analogy. This firewall, positioned at the edge of the network, filters traffic between the internal network and the external internet.
And since traffic flows in both directions, you need to consider both incoming and outgoing traffic.
Absolutely. You might want to restrict outgoing traffic, to prevent users on your network from accessing certain websites, maybe for security reasons, or to just limit distractions.
Like having neighborhood rules about what activities are allowed and where people can go.
And for incoming traffic, you'd likely have a similar default deny policy.
Okay.
Only allowing the essential traffic needed for your network to function properly.
It sounds like setting up firewalls effectively requires a really good understanding of network protocols and the services running on your network.
Yeah, and best practices for security.
Yeah, like becoming a network security expert.
It does require some expertise.
Yeah.
But the good news is there are plenty of resources available to help you learn and implement solid firewall strategies. It's well worth it because a strong firewall can significantly reduce the risk of your systems being compromised.
It's like investing in a good security system for your home.
Exactly. Gives you peace of mind.
So, shifting gears a bit, our sources also touch upon this really interesting aspect of Linux, its use in embedded systems.
Embedded systems, yeah.
These are like the brains behind all sorts of devices, right? Smartphones, smart TVs, even cars.
You got it. Embedded systems are everywhere these days.
They are.
Quietly controlling the devices we rely on. And Linux, with its open source nature and flexibility, has become a popular choice for developing these systems.
Our sources highlight how Linux's open source nature is a big advantage for embedded systems development.
Imagine having a blueprint that you can modify to fit your exact needs.
Right.
That's what open source offers. Developers can access and modify the Linux source code to perfectly tailor it to the requirements of their embedded device.
And because Linux is known for being so lightweight and efficient, it can run well on devices with limited resources, which is often the case with embedded systems.
Exactly. You don't need a powerhouse computer to run a smart thermostat or a simple network-attached storage device.
Right.
Linux can handle those tasks with ease.
Plus, the fact that Linux has such a large and active community means developers have access to a wealth of knowledge and tools and support.
It's like having a global team of experts, right?
Yeah.
Ready to help you troubleshoot problems and share their insights.
It's really amazing to see how Linux has become so pervasive, powering everything from these tiny embedded devices to those massive server farms that handle huge amounts of data.
It's a testament to the power of open source and the collaborative spirit of the Linux community.
Well, expert speaker, it feels like we've reached the end of our Linux journey today. We covered so much ground.
We have. We've explored the Linux landscape from top to bottom, from its core architecture to its vast networking capabilities and beyond.
We've seen how Linux, with its elegant design and robust features, has become such a dominant force in the computing world.
From its humble beginnings, as a personal project, to its current status as the backbone of the internet,
Right.
Linux continues to evolve and inspire.
We hope this deep dive has given you, our listener, a much deeper understanding of this remarkable operating system.
Perhaps we've sparked your curiosity to explore further, to tinker with a Linux system yourself.
Yeah.
Or even contribute to the open source community.
There's always more to learn in the world of Linux. We encourage you to keep exploring.
Keep diving deeper.
So until our next deep dive, keep that spirit of curiosity alive. And remember, the world of technology is always open for exploration.